Hello, this is our second discussion on common mistakes that students make when they write compound names and formulas. We'll be focusing on looking at common mistakes with writing oxides, hydroxides, or peroxides, or recognizing which is which in a chemical formula. We'll also be looking at some relationships with binary acids and ternary acids when you're naming them, making sure you use the right prefixes and suffixes. We're also going to be considering how acids can sometimes be related to polyatomic anions, which have similar formulas but fewer numbers of hydrogens in the formulas. We'll also look at when we might use prefixes on ionic compounds and how that differs from prefixes that are used in molecular compounds. So first of all, let's look at oxides, hydroxides, and peroxides. We'll look at several examples of these. So if I'm talking about the oxide anion in an ionic compound, similar to what we would be looking for if we had iron 2 or iron 3 oxide forming with respect to a rusting process, the oxide anion is oxygen with a 2- charge. Now I can predict it has a 2- charge because it is 2 away from the nearest noble gas, neon, and if it can gain 2 more electrons, it's going to have the same electron configuration as neon, the same valence electron shell as neon, so it gains extra stability. So that would be our oxide. Now, if I have a few compounds that have oxides in them, we'll be looking for the oxygen having a 2- charge. So for example, if I see the following ionic compound, I see my metal cation would be the sodium cation, and the charge on a sodium cation will always be the same. It's stable as a +1 charged cation, so we would end up with having 2 of them in this formula, so my overall positive charge is a +2. So if that's the case, my anions must balance that charge out. Since there's only one oxygen atom, it must have a 2- charge and be oxide. So I would name this as sodium oxide. No Roman numeral is needed for the metal cation because only one possible charge is available for a stable sodium ion. Now if we consider the following ionic compound, I can tell it's an ionic compound because I have the aluminum cation and I have oxygen present. Let's confirm that oxygen has a 2- charge and is an oxide. So if we consider that aluminum will always have a 3 positive charge, and there's 2 present here, so a +6 total, and that we have 3 oxygens balancing that charge, they must each have a 2-, so that would add up to a 6- total, so that my overall ionic compound formula would be neutral. If each oxygen has a 2- charge, I must have an oxide, so I would have aluminum oxide. Okay. Here I have magnesium. Magnesium is a group 2 metal, so that's an alkaline earth metal. They all form a 2+ charge by losing 2 electrons. They have the same number of electrons as the nearest noble gas before them. Since magnesium has a 2+ charge in this compound, the oxygen must also have a 2- to balance out charge, so this would also be an oxide, so I'd name this as magnesium oxide. None of these metals need a Roman numeral in their name because they have only one possible stable charge state. Remember, when we're dealing with transition metals or metals under the metalloid line that have a variety of possible stable charge states, we would use Roman numerals in those cases. So here I have the metal tin, and I have my oxygens. Now, if the oxygens are oxide here, which is what I'm predicting, I would have a total of 2 oxides, or a 4- total, so the tin would have to be a 4 positive to balance charge. The common stable charge states for tin are 2+ and 4+, so this would fit what I would predict. So I could name this tin 4 oxide. Now when I see hydroxides in compounds, I want to be careful not to confuse that with oxide. My hydroxide formula is an OH-. We'll see this in a lot of bases in the course. If we realize that hydroxide has a hydrogen as part of the formula, it has just a -1 charge. Well, those hydroxides, when I'm looking at compounds, the hydroxide will usually be written second as the anion, and the metal cation will be written first. So if I see the following formula, this is one of my common strong bases that you should be learning. I have the sodium cation. The charge on sodium is a +1, hydroxide is a -1, so I need only one hydroxide in the formula. So this would be sodium hydroxide, no Roman numeral needed because sodium only forms +1 charges. It's a group 1 alkali metal. Now if I have the calcium cation, though, it's an alkaline earth metal in group 2, it would lose 2 electrons to form a 2+ charged cation. I would need 2 hydroxides. And remember, when we have a polyatomic ion, we want to show the polyatomic ions if there's more than one of them in brackets. And outside the brackets, we put a subscript 2 that indicates there's 2 entire hydroxide anions present to balance the charge on the calcium cation. I can merely name this calcium hydroxide. Again, no Roman numeral needed because calcium is only stable as a 2+ charged cation. If we consider the following ionic compound, now we have iron. So now iron can have a variety of stable charge states. The most common charge states that are stable for iron are a 2+ and a 3+. Here we have 3 hydroxides. Since they're a -1 each, I must have a total of -3 from all the anions. So the cation must be a +3. So I would use Roman numerals in this case since iron can have a variety of charge states. So I'd name this iron 3 hydroxide. Now, if I have the peroxide anion, I would have 2 oxygens as a polyatomic ion here with a 2- charge. I often have to look at the cation to see how it's balancing out. So if I were to have a metal cation that was balancing out 2 oxygens with only a +2 charge, well, that must be a peroxide. If I was seeing that the charge on the anion would have to be a -2 per oxygen, we might have something like an oxide, like we saw here with tin 4 oxide. So let's look at an example of some peroxides. Now, peroxides tend to be quite reactive. Here's a molecular compound that has peroxide in its name. We'd call this hydrogen peroxide. Here's an ionic compound, which is a little bit easier to look at the charges and determine that we have a peroxide. If we look at sodium, I have 2 sodiums here, so I must have a +1 charge for each sodium. So since there's 2, I have a total of a 2+ charge. So the oxygen would be a 2- for the overall O2 group. So that would only occur if I had a peroxide. So this would be a sodium peroxide. If this were sodium oxide, I could tell the difference because I would have required 2 sodiums for 1 oxygen, as we had seen earlier for sodium oxide. So by seeing the charge balance, I can tell if I have a sodium oxide versus a sodium peroxide. Those are common mistakes I see made with respect to recognizing the differences, so be careful there. Here we have barium. Now, barium's an alkaline earth metal underneath strontium in group 2. Has a 2+ charge. Since that 2+ charge for 1 barium cation is still balancing the charge of my 2 oxygens here, that's my hint that I have a peroxide. So this would be barium peroxide. If it were barium oxide, we would only have 1 oxygen there because we'd have a +2 on the barium, and an oxide would have a 2-, so only 1 oxygen would have been needed from oxides. So that's how I can tell the difference there. Now let's look at a few molecular compound names that have the ending that is an oxide. Now realize these are molecular compounds, they are not ionic compounds. So be very careful, even though we're using the "ide" ending, we're not talking about this monoatomic anion of oxide. So if we consider some non-metal oxides that are molecular compounds, we could have 2 nonmetals combined, no ions present here. I would use my prefixes to determine the number of atoms in a molecular compound. So I should name this as a dinitrogen, since there's 2 nitrogens, and there's 5 oxygens, so I'm going to call this a pentoxide. Now remember, when we have 2 vowels adjacent to one another, we will often drop the vowel off the prefix. So here we have pentoxide, where the A as a vowel has been dropped. So dinitrogen pentoxide. So here's another common molecular compound that would have oxide in its name. This is carbon dioxide. So when I see these Greek prefixes, that's telling me that instead of having oxides in an ionic compound, I'm expected to have a molecular compound. So those prefixes give me a lot of useful information. Remember, don't use these Greek prefixes usually with ionic compounds. So if you do so, you're usually naming them incorrectly. So do only use these Greek prefixes with these molecular compounds we're looking at right now. I will mention a brief exception about this towards the end of this discussion. But for right now, don't use those Greek prefixes on ionic compounds. So here's another molecular compound. We have sulfur and 3 oxygens. There's no charge shown, so this would be a molecular compound here. So we have 1 sulfur and 3 oxygens. Remember the first element, just like we saw in carbon dioxide, if there's only 1, we usually omit the Greek prefix. So again, I do that here. So I just have sulfur. But the second element, we always use our prefixes. So I'm going to use a tri for the 3 oxygens. So it's a trioxide, sulfur trioxide. The next thing that we would like to look at is comparing binary acids versus ternary acids. So my binary acids will have usually just two elements present, hydrogen and a secondary element. So here I have a binary acid with hydrogen and chlorine. A ternary acid would have three elements. It would have hydrogen, oxygen, and a third element. Okay, so as I'm looking at naming these binary acids though, I want to use the prefix hydro, and then I use the element name that's combined with hydrogen here, and then the end of the name is always acid. So I have hydrochloric acid in this case. Now I name this compound, this molecular compound, as an acid when it's in water. If I had this in the gas phase, we would actually name it as a molecular compound. Sometimes you'll hear it called hydrogen chloride or hydrogen monochloride using our Greek prefixes in the gas phase. But once it's in water, we name it as an acid. Unless I tell you otherwise, it's perfectly acceptable on our exams to assume that you have an acid and write the acid name down, unless I have the phase label of a gas on that formula. Here I was very specific. I told you it's an aqueous solution. We're in a water-based solution, so we're naming it as hydrochloric. When I see this prefix hydro, you need to remember that's binary acids. We do not predict them to have oxygens in the formulas. If I have an oxygen in the formula, we're going to name the acid as an oxo acid, as I mentioned in our previous tutorials. So be very careful there. So here we have a similar formula. There's hydrogen and one chlorine, but three oxygens. So now I do not use the prefix hydro once I see oxygen in the formula. I'm going to name this compound chloric acid. Do not put hydro in the beginning, or we think there's no oxygens, and it would be the binary acid hydrochloric acid. So I want you to recognize, if you look at the end of the chloric acid formula, the ClO3 looks a lot like our chlorate anion. So when you kind of see that formula that looks similar to the chlorate ion, the 8s go to Ix when they're acids. So this is chloric acid. Here's another binary acid, HBr. So we use the prefix hydro. So here we'd have hydrobromic acid. If I have an oxygen in the formula, this looks similar to the bromate ion at the end of the acid formula here. The hydrogens at the beginning are equivalent to whatever charge you would have thought of in the anion. So if I have bromate, I'm thinking bromate has a -1 charge. When I start looking at an acid that has that as part of the formula, we'd have one hydrogen at the beginning. So we'd end up with naming this as a ternary acid. So I do not use the prefix hydro. Since I think about bromate being as part of the formula, I realize those 8s go to Ix, so I call this bromic acid. Here we have H2S. Now H2S in water would be named as hydrosulfuric acid. Remember, the hydros are all used here in these binary acids where there's hydrogen and a second element and no oxygen. So there's only two types of elements in the formulas. If I had this in the gas phase, I might call this dihydrogen sulfide or dihydrogen monosulfide, or just hydrogen sulfide is a common name, but I might try to name it as a molecular compound in the gas phase. Now if I add my oxygens to it, so if I have hydrogen, sulfur, and 4 oxygens, this looks a lot like the sulfate ion. So if I'm seeing that formula that's similar to sulfate, when it forms an acid, the number of hydrogens is equivalent to whatever charge you remember for the sulfate ion. So sulfate has a 2- charge. So when I have this acid, I would need 2 hydrogens. We would not use the prefix hydro since it's not binary. So I would go ahead and name this. The 8 form here goes to an ic in the acid, so I name this sulfuric acid. Okay. If we look at HCl, that's another binary acid. That would be in the gas phase we name this as hydrogen monochloride or hydrogen chloride. Okay. If it's in solution, in a water-based solution, we call it hydrochloric acid, as we see here. If I have H2S in the gas phase, as I mentioned before, we might call this dihydrogen monosulfide, sometimes called dihydrogen sulfide or hydrogen sulfide without using our strict prefix naming rules. But this is the strictly correct name when we're using our correct prefixes, so dihydrogen monosulfide. So realize there is sometimes a difference in the naming of our binary acids in water versus in the gas phase. Realize I should use hydro with my acids only when they're binary acids with hydrogen and one other element. When I have hydrogen, an element, and oxygen in the formula, we're going to be using the endings for the acids of Ix or Us's. If you notice that the anion would have had an ate in the ending, we go to ix with the acid form. If the anion would have had an ite, we go to us's. But these all were ate anions if you think about the end of the formulas here. So we went to chloric, bromic, and sulfuric acid. Okay, now let's look at a few oxoanions and compare them to acids to look at their names. So here, if we have the carbonate ion, I've asked my students to learn the formula. So that's going to be carbon, the number of oxygens. In this case, we're going to have 3 oxygens in the formula, and the charge, which is a 2-. So you should know carbonate as an anion is written as CO3 2-. Now, if I have the carbonate ion, if I were to write an acid that's related to this form, I would need to have 2 hydrogens. Since the charge of the carbonate ion is 2-, the acid form would have 2 hydrogens in it, and I would name it carbonic acid. So my 8's go to ix. So carbonic acid is H2CO3. If we consider the nitrate ion, you should remember that it's nitrogen, 3 oxygens, and a -1 charge. If we had the acid form, since the charge is a -1, we'd only have 1 hydrogen in the acid. So we would also name this acid, since there's an 8 in the oxoanion, we would name the acid with an ic at the ending. So I would call this nitric acid, with that ic at the ending, and we'd have just the 1 hydrogen there, so we have a neutral molecular acid. We have HNO3 for nitric acid. If we looked at the nitrite ion, you remember as you go from 8s to ites, you should have 1 fewer oxygen in the polyatomic oxoanion. So here we have NO2 with a 1- charge. If we form the acid again, we need just 1 hydrogen, but since we're not going from an 8, we don't go to ic. Here we're going from an ite, so we need to go to an us ending. So I would call this nitrous acid, and it would have the formula HNO2, just 1 hydrogen in the formula. Now if we look at sulfate, I should remember that sulfate has sulfur, 4 oxygens, and a 2- charge. So that's what I've written here, sulfur, 4 oxygens, and a 2- charge. If I have the acid form of this ion, we'd have to have the number of hydrogens at the beginning equivalent to whatever the charge was here. And so I would name that, since I'm going from an 8, I go to an ic again, right? So I would name that sulfuric acid. And when I write the formula, I have H2SO4, again 2 hydrogens, same number of hydrogens as the charge we first saw on the anion. Now if I have sulfite, just as we saw with nitrate, as we went from nitrate to nitrite, we had lost 1 oxygen from the 8 form. Now here we begin with sulfate with 4 oxygens rather than 3, but still as I go from an 8 to an ite suffix here, we end up with 3 oxygens. The charge is maintained in the whole series, as you would have remembered from my previous tutorials. And so if we go ahead and look at the naming of the acid, we need 2 hydrogens because the charge was a 2-. Since I'm going from an ite instead of an 8, 8's go to ix, remember. If I'm going from an ite, I need to go to us's. So I should have sulfurous acid, and it would have a formula H2SO3. So you have to pay really close attention to the number of oxygens, because the suffix that's added to my element name has a very specific meaning with respect to the number of oxygens. So if I were to name these incorrectly with the wrong suffix, I would get that incorrect on a question. Now if I have phosphate, I should recognize that phosphate is phosphorus, 4 oxygens, and a 3- charge. You need to have all of these 8 oxoanions memorized. These are very common ones. You should then work on the rest that are in our class lists, but this is a good set to begin with. The phosphate anion, since it's a 3-, if I have the acid form, how many hydrogens should it have? I hope you answered 3, right? Since I'm going from an 8, what suffix should I have on the acid name? Hopefully you said an ic. So this would be phosphoric, since I'm going from an 8 form. So it's phosphoric acid. And I'd have H3PO4, 3 hydrogens, equivalent to the charge on the original anion. So these are some very common acids. If I had phosphorus acid, what would be different in the formula? If I had phosphorus acid, I would have 1 less oxygen. So phosphorus acid would be H3PO3. If I ended up looking at the anion there, that would be the phosphite anion. It would be PO3 3- if I were considering that. Okay, I have one more question for you. If I were to have hydro in any of these names, that would be incorrect. A hydro, if I had hydro Chloric acid, for example, I would not have the chlorate anion. I would just have chloride as at the end of the formula. So here we have no hydros because none of these are binary acids. They all have oxygens in them. So I better be seeing you not use hydro and use your us's and your ics and the end of your acid names when you have oxygens present. Okay. Now this is a common anion that I see students forget, so I'm certain to probably put it on assignments and tests to make sure you learn it. The best thing here is just to learn that this is the acetate ion, C2H3O2. Now sometimes this can be a little confusing seeing acetate ions in formulas and chemical reactions because sometimes we'll write them to show a little more structural information. We might show that the carbon is bonded to 3 hydrogens and then bonded to another carbon. This carbon is bonded to 2 oxygens. It's actually double bonded to one of the oxygens and single bonded to the other, and it has a -1 charge overall. So these are other formulas for the acetate ion. We might also write it as CH3. That should be a subscript 3 there. CO2 minus. So these are all different ways of writing the acetate ion. You should remember that this is an anion and be able to recognize it, be able to write its name and its formula correctly. I'm okay if you pick any one of these ways of writing the ion formula as long as you have the right number of atoms of each type, 2 carbons, 3 hydrogens, and 2 oxygens, and a -1 charge. Now, if we look at that charge of a -1, if we had a hydrogen in front of this formula and a neutral charge, well, that would be an acid formula. It's a slightly different acid formula than we've seen before. This one actually has 4 different elements. Actually 3 elements, I'm sorry. But it has hydrogen, carbon. Now it has a second grouping of hydrogens. This is the acidic hydrogen shown at the beginning of the formula, and 2 oxygens. So this is also considered an acid, and we give this the name acetic acid. So again, the aid is going to an ic. So we have acetic acid. Sometimes the acetic acid is written with the acidic hydrogen next to this oxygen that has a negative charge in these 2 forms. So I might write it as CH3COOH or CH3CO2H. This just gives me more structural information about the acid, and it shows me where the acidic hydrogen is, so I can differentiate it from the hydrogens that are not considered acidic in this compound formula. So this one you often have to memorize. It's one that is sometimes hard for first-time chemistry students to learn, so make sure you work on that one because it is a very common acid. It's present as a dilute solution in water, in vinegar in your kitchens, or in vinegar salad dressings, so you're dealing with it quite frequently. Now, if we see the following anion, I have chlorine and 4 oxygens and -1 charge, I need to be thinking about the proper name for this. Hopefully you've learned that the formula for chlorate is ClO3-, so this has 1 more oxygen than chlorate. Since it has 1 more oxygen, we need to add a prefix. So as we go from chlorate to 1 additional oxygen, we add the prefix per. So I would name this perchlorate. Now the charge is still a -1, just like chlorate's charge was. If I had the acid form, we'd have 1 hydrogen in front and the charge would be neutral at that point. So here's an acid form of it. So again, we have hydrogen and the chlorine and 4 oxygens. Now I can't call this chloric acid because chloric acid would have only 3 oxygens. So since I have the per here, I'm going to maintain the per in the acid name, but change the 8 to an ic so I know I have an acid. So I have perchloric acid. So I just changed the 8 to an ic again, just like we did with the acetic acid when we changed it from 8 to ic for that name. But I always keep the prefix here, so I have perchloric acid. Now if I had 1 less oxygen, hopefully you've memorized that as my chlorate. Again, I don't need to use a prefix here. I need 1 hydrogen because the charge on the anion was a -1. So I would end up having chloric acid as my formula. If I had 1 less oxygen than the 8 form, we'd go to ites. So chlorate goes to chlorite once we have only 2 oxygens present. Notice the charge is the same in the whole series. So this is chlorite. And if we have the acid form, we need 1 hydrogen in front, just like we saw in the rest of the series. So this one goes from an ite to an us. So I would call this chlorus acid. Remember, 8s go to ics. We keep a prefix if there's 1 there. And ites go to us's. Okay, let's look at one more example here that's similar. If I drop an oxygen from the chlorite form to go to just 1 oxygen here, we end up having to add a prefix. So we keep the ite, but we add a prefix. We indicate hypochlorite, hypo meaning below, and we end up adding 1 hydrogen to the beginning of the formula. When we add the acid, when we write the acid formula. So now I keep the prefix, but the ite goes to an us. So I call this hypochlorous acid. So be very comfortable writing these series of acids from your series of oxoanions that you've been learning. You're expected to be able to name any of the oxoanions in a series using knowing your chlorate form, having that memorized. If you have an extra option, you would say it's per-8 with the element name in the middle. If we have one less option, the 8 goes to an ite, so it's an element name ite. If we have one less option than the ite form, we go hypo element name ite when we're naming them. Okay. The acid forms, just remember they keep the prefixes that they're there, like the per or the hypo, but the ates in the name of the anions go to ix in the acid formulas, and the ites in the name of the anions go to us's in the acid formula. So that's going to help you predict quite a few different names and formulas for ions as well as acids. So these will all be on the exams in the course, the final as well as the exam on this chapter, so make sure you keep up with learning these rules. Okay, let's look at a few other anions and their acids. So this is the carbonate anion. Carbon, 3 oxygens, and a 2- charge. Since that's carbonate, if I had an acid with the same number of atoms present, carbon and 3 oxygens, I would add 2 hydrogens to the front because there's a 2- charge. Now this is an 8 without any prefix, so there's no prefix, there's the element name and then an 8. So the acid formula would have to have 2 hydrogens, and I would name that carbonic acid. Now there's no reason why I have to add both hydrogens all at once. So what if we only add 1 hydrogen to the formula? Now when I add 1 hydrogen, I will decrease the charge by 1, so here it's still a -1. This is a special polyatomic ion that you need to learn how to name. Now here's a case where I will name an ionic compound that contains this, the cation, but then I need to give a name to this ion, which is going to be different than the carbonate ion because of the hydrogen. So I need to name this hydrogen carbonate. It's also commonly called in our society bicarbonate. So we have hydrogen carbonate or bicarbonate. Either name's acceptable. I think it might be a little easier for you to remember hydrogen carbonate because you see the hydrogen at the beginning of the formula. Now, if I have the 2 hydrogens, though, we have no charge shown. This is the acid form once we've added the 2 hydrogens, so we call this carbonic acid. It would not be correct to call this dihydrogen carbonate. Okay, we will not do that for this species. We just call it carbonic acid. So be very careful to not try to use your prefixes in this case. Now, if I look at sulfate, sulfate can do the same thing as carbonate with respect to having only 1 hydrogen on the anion. If we add 1 hydrogen onto sulfate, we have hydrogen, sulfur, 4 oxygens. The charges drop by 1 every time we add a hydrogen to the formula, so we still have a -1 charge. So this is another polyatomic anion you need to remember the name of. This would be hydrogen sulfate, sometimes called bisulfate in our society. I'm fine if you use the term hydrogen sulfate. I think that's a little easier for you to remember, but be able to recognize the term bisulfate here just like you have to recognize bicarbonate as just 1 hydrogen on the carbonate ion. So bisulfate has 1 hydrogen on the sulfate ion and the charge is decreased by 1. Okay, now if I add 2 hydrogens, our charge drops to 0. We predict once that charges drop to 0 with those 2 hydrogens added, they're acidic hydrogens. We now have the acid name. Since this was a 8 in the sulfate, we go to an ic for the acid, so we name this sulfuric acid. Okay. Let's go ahead and look at a third anion that has a charge that's greater than 1. This is going to be phosphate. So phosphate has phosphorus, 4 oxygens, and a 3-. Now, how many hydrogens can I add before I get to the acid form? Hopefully you recognize we could add 2 hydrogens and still have a charge maintained. It's not until we hit the 3rd option that we get to phosphoric acid. So let's add 1 hydrogen. So this is the phosphate ion. If I add 1 hydrogen to it, I give this polyatomic ion a special name. I need to indicate that hydrogen, so I call this hydrogen phosphate. Okay. Now, however, if I add another hydrogen, notice the charge is dropping by 1 with each hydrogen that I add. If I add another hydrogen, I have 2 hydrogens here. We have a -1 charge still, so this is still a polyatomic ion. Be very careful. This is not the acid form yet, so I don't name this as an acid. I'm going to indicate that I have the 2 hydrogens. Now sometimes this is confusing because we're going to use a prefix to indicate the 2 hydrogens even though this is not a molecular compound. This is an ion. This is an anion. So this is one of the few occasions where you'll see a prefix that's for a number of atoms in an ionic compound when we have this specific polyatomic ion. So I could name this dihydrogen phosphate even though it's still an anion. So if I had, let's say, sodium dihydrogen phosphate, I'd have sodium here balancing the charge and the -1 charge. I'd call that sodium dihydrogen phosphate, and it's one of the few times I would use one of those prefixes. Now if I add a 3rd hydrogen, my charge drops to 0 and I name it as an acid. Since we begin as an 8, we're going to name that as an acid with an ic ending, so this is phosphoric acid. Okay, so I just want you to realize this is one of the few cases where we're going to see prefixes of di in an ionic compound. So be careful of that exception. You'll also be seeing the bisulfate here and the bicarbonate. So that bi again is not relating as a prefix to a molecular compound. These are all ionic compounds. So these are some exceptions that can sometimes be a little confusing. Common mistakes that I see when you're writing these formulas. Also realize when I'm writing out the names for these, I don't want to add prefixes when they're not needed. So I don't name this as dihydrogen carbonate when I have carbonic acid. Okay, the next thing you need to remember, a very common error is that when students write the formula for ionic compounds, they will sometimes accidentally use prefixes. So don't use prefixes when you name ionic compounds. You should use your prefixes when you name molecular compounds. The only exceptions we have seen now are when the specific anion has a prefix needed, like the dihydrogen phosphate, or if I'm using the bisulfate prefix or bicarbonate prefix. Unless I have those scenarios, I would predict for my common ions that we're working with in this course that I wouldn't use those prefixes. So normally when you see the prefixes, they're molecular compounds, but keep your eye out for the hydrogen carbonate or bicarbonate and the hydrogen sulfate or bisulfate and your dihydrogen phosphate. Those can sometimes be a little confusing because of the prefix used. Normally the prefixes are only used for molecular compounds other than those exceptions that you're learning right now, and a few other ions that we're not looking at currently. Okay, so let's compare some different polyatomic ions that would have the bi or the di prefix here. So first of all, this is an interesting polyatomic anion because it has a metal as part of the formula of the polyatomic ion. So you need to learn that the name of this species, when there's chromium of 4 oxygens and a 2- charge, this is the chromate ion. Now the reason I'm bringing up the chromate ion is we're going to see a very similar ion in just a moment that uses a prefix. Now if I have the following formula with 2 chromiums and 7 oxygens and a 2- charge, this can often form. This ion can form often if I have chromate in solution in an acidic solution. The chromate's yellow, but I can in acidic solution start to form this ion, which is an orange color. Now this is my dichromate. So here I'm using a Greek prefix to indicate the 2 chromiums even though I still have an anion. So be very careful. We kind of broke our rule here when we said that ionic compounds shouldn't use prefixes. So sometimes we do if we need to indicate multiple elements that are present of an oxoanion. So we have to be careful there. Now if I have PO43-, we've just looked at that recently, that's phosphate. Okay, remember as we saw before, if there's 1 hydrogen, we would name that as hydrogen phosphate. If there's 2 hydrogens here, now we use a Greek prefix dihydrogen phosphate. So even though these are polyatomic ions, we're using some Greek prefixes. This is really the only occasions you should be predicting right now where you use those prefixes with any ionic species. The rest of your ionic species that you haven't learned any prefixes for the polyatomic ion name will not be using Greek prefixes, so be cautious. Okay, so now let's look at a few molecular compounds. If I have carbon dioxide, now this Greek prefix, since I just have non-metals for a molecular compound, is telling me the number of oxygens in the formula. So here I have CO2, not an ionic compound. The di here does not indicate the number of hydrogens in a polyatomic ion. It's just a neutral molecule, so be careful. There's a difference there. Now if I write dinitrogen pentoxide, once I see these multiple Greek prefixes, that should be screaming in your head. This is a molecular compound. I'm indicating the number of nonmetal atoms. Okay, so you need to keep track of that. So I'd write this as dinitrogen. It has 2 nitrogens in the formula, so I shows as a subscript after the nitrogens element. It's a pentoxide, the pent indicating 5 oxygens, so I write that as a subscript after the oxygen. Okay, so once I start to see multiple prefixes, you should stop and say, is that a molecular compound? And you should be thinking most likely, unless I see one of these very unique prefixed ions, like dihydrogen phosphate, dichromate. I might see a bicarbonate, right, or a bisulfate. Okay, but those are the only cases you should be looking for right now. So if I see the bicarbonate ion, sometimes called just hydrogen carbonate, this is actually a polyatomic ion, so be cautious. So that's HCl3 with a -1 charge. It would still need at least a positive charge from a cation to balance out the charge. If I have the bisulfate, which is also known as hydrogen sulfate, well, now I have another polyatomic anion, HSO4 with a minus charge. So be careful with these more complex polyatomic ions that you're learning right now. Sometimes we will use prefixes. The bis for bicarbonate or bisulfate, or the dis for dihydrogen phosphate, or the dichromate. Okay, we might see dis with some of our molecular compounds. If I just see nonmetals and I don't recognize it as a polyatomic ion, or if I see other prefixes in the formula, it's a dead giveaway. That should be a molecular compound. Okay, so be very cautious with these. If you continue on in chemistry, you'll see a few other ions that will use some of these prefixes, but right now these are the only ones you need to learn. So very common mistakes that we're seeing in these tutorials are when we can frequently accidentally mix up some of our rules. So these are very common ones that I see errors with, so we're looking at some more complex concepts. So make sure you learn these so that you're ready for our exams and quizzes. Okay, keep looking at our schedule to see when our next exam is, and good luck. Thank you.